So now we've talked about the temperature of our protoplanetary disk and why the inner planets are rocky and the outer planets are more gaseous and icy. And here we're going to talk a little bit more about how the core of those planets formed in the first place. Okay, and so this little segment is going to be about planet formation. Here we have our protoplanetary disk. We can have iron and silicates that are condensing in the inner part of the solar system, and we've got waters and ices that are condensing in the outer part of our solar system. Okay, and what happens is that as that material orbits around the solar system, some of that material begins to smash into each other. And that's a process that we call accretion. Initially, tiny particles in our early protoplanetary disk are going to stick together due to the electrical forces between them. But once these objects get large enough, they will be attracted together through gravitational forces, and they're going to start to form larger and larger and larger objects, okay? And then those larger objects are going to collide into larger objects, and again, it's sort of like a snowballing effect to grow a planet. So accretion leads to objects that we call planetesimals. Planetesimals are baby planets. These planetesimals range in size from millimeters in size to kilometers in size. And these planetesimals are what eventually become planets, or if they don't grow large enough, they become asteroids or comets. We do have evidence of this accretion process, and that evidence comes in the form of meteorites, okay? So meteorites are fragments of larger bodies called asteroids that are found on the surface of planetary bodies. An asteroid is basically a space rock. It ranges in size from 1,000 kilometers to 1 meter across. These asteroids are essentially leftovers from the formation of our solar system that didn't get to combine in order to create a planet or a moon. So when an asteroid enters the Earth's atmosphere, they're called meteors. That's the streak shooting star that you see in the sky, okay? The asteroid coming into the Earth's atmosphere, there's a lot of friction between that asteroid and the Earth's atmosphere that creates heat, and that creates a glow that we see as the meteor streak in the sky. And when that bit lands on the Earth, we call them meteorites. Okay, so that's the difference between a meteor is still in the Earth's atmosphere, a meteorite is on the ground, and it's an asteroid when it's in space before it enters the Earth's atmosphere. If you take one of these meteorites and you slice it in half, this is what they look like. Okay, here's sort of like a cross section of a meteorite, and you can see how there's these little pebbles that kind of look like concrete, but they've been sort of like smushed together and mixed together to create a larger body. That's the process of accretion that's causing what you see here, okay? And then if you zoom in, each one of these little kind of blobs is something that we call a chondrule. These planetesimals, these baby planets, in the inner solar nebula, the inner protoplanetary disk, were the rocky iron composites for the reasons we already talked about, while planetesimals in our outer solar system were icy, rocky iron composites. Icy because you're further out from the sun, it's a little bit colder out there. The planets formed from more gentle collisions of these planetesimals, which tend to dominate over more violent shattering collisions, which would, if you slam into something really, really hard, you're going to smash it into a bunch of million pieces, okay? But if you come in and it's just like a gentle kind of collision on the objects on each other, they can kind of stick together. And so that kind of sticking together is what over time grew these planets, okay? The planet growth was especially fast in our outer solar system due to the larger volume of material that's out at the edge of our solar system. Why is there more material out there? Well, just think about the disk, okay? If you think about closer to the disk around the sun, if an object is orbiting around that disk, when it's closer to the sun, that orbital path is smaller, okay? The circumference of that path, or the length of that path, is the circumference of a circle, which is 2 pi times the radius, the distance from the sun. So that number is small, close to the sun, okay? And when you get out towards the edges of our solar system, that orbit is larger. So that distance around which you're orbiting the sun, that distance is still the circumference of a circle, 2 pi r. But now the radius, the distance between the sun and that planet is much bigger, so that circumference around which, or that path which you're orbiting the sun with, is longer when you're getting out to the edges of our solar system. So that means you have more material to move through. And that's why you can build these larger planets further out away from the center of the sun. Okay, so that explains why there's a larger volume of material in the outer protoplanetary disk than there is in the center. And these larger objects, larger than Earth, out at the edge, or towards the edge of our solar system's protoplanetary disk, could start to gravitationally capture those gases like hydrogen and helium, okay? So these gases, when they heat up, they start to bounce around and they gain energy and they have a speed associated with that energy. So when those gases are very close to the sun, like our inner planets, those gases are going to be bouncing around much faster. It's going to be harder for those smaller bodies in the inner solar system to be able to hold on to that rapidly moving gas, which explains why they don't have such a great atmosphere, such a large atmosphere. But then whenever you get out towards the edges of the solar system, you know, it's colder there. So that gas is not bouncing around as fast. And so it's easier for those planets, which happen to be a little bit larger in their core anyway, to be able to hold on to that gas, which isn't moving around as rapidly because it isn't as hot. And so that explains why our outer planets also have such thick gaseous atmospheres. Those are our gas giants like Saturn and Jupiter. Here's another figure that talks a little bit more about planetesimals and how they form planets. So in the early accretion process, we've got a bunch of planetesimals that have crisscrossing orbits around as they're going around the sun, and more of them start to slam into each other. They start to accrete onto each other. And as time passes, you have fewer planetesimals because more of them have merged into one, and we slowly start to grow our planets, okay? And so we can grow our planets by accreting smaller planetesimals onto the larger planetesimals, while collisions between very large planetesimals could cause those objects to shatter and break apart into smaller pieces. But if you have a large planetesimal and it's being in a collision with a smaller planetesimal, that smaller planetesimal colliding with that much larger planetesimal probably wouldn't shatter the larger planetesimal, and then you can start, you know, kind of growing like a snowball again. So ultimately, only the largest planetesimals were able to avoid collisions that didn't cause them to shatter, and were able to grow into our fully fledged adult planets. In the final stages of our solar system's formation, we had what's called the bombardment period, okay? So you had a rain of planetesimals that were kind of left over from the formation of the other bodies in our solar system, and they cratered the surfaces of some rocky bodies. The remaining planetesimals that didn't sort of crater the surface of some of the other rocky bodies became small moons, comets, and asteroids. These planetesimals continue to bombard things like Mars, like Mercury, and internal radioactivity melted the planets and led to the density differentiation of planetary interiors. So this is kind of a little bit about what happened on the moon too. The early moon was bombarded by a lot of these planetesimals, rain of planetesimals, and it heated up the moon, and it caused some lava flow, some kind of volcanic activity on the early moon too. Moons of our outer planets were probably formed from planetesimals orbiting the growing planets. So, you know, like for instance, Jupiter and Saturn, they probably were able to capture with their gravity some of these planetesimals, and then those planetesimals could also start to accrete with each other as they're orbiting around the planet, and that leads to some of the moons that they have out there too. Well, one way we can estimate the age of surfaces is by counting the number of impact craters on it. This only works, of course, for our rocky bodies in the solar system. The rate of impacts in our solar system has been roughly constant for several billion years. So the older a surface, the more it's going to be impacted by craters. The older the surface, the more cratering it should have. Okay, so if we observe the moon, parts of the moon that have more impact craters are parts of the moon that are older than the parts of the moon that have less impact craters. Okay, that's what that means. Or if we observe Mars, parts of Mars that have more impact craters should be a part of Mars that's older than other parts of Mars that don't have as many impact craters. Okay, so a great example is the moon. Here we have the moon, and we see that there's way more cratering in these white patches, which are the older surfaces of the moon, than there are in these dark patches. There's less cratering in these dark patches. Why? These dark patches are called the maria. It's plural for seas. Latin for seas is maria. Singular is mare. And it's dark here because in the moon's early years, there was some volcanic activity, and lava flow filled in parts of the lunar surface. So this, and this dark material is, well, the reason why these regions look darker is because that material has a different reflectivity than the other parts of the lunar surface that appear to be brighter. Okay, these darker patches are made up of a rock called basalt, which is a rock that can be formed from volcanic activity. And the reason then again why there's not as many impact craters here is because this surface is younger, because the older impact craters were filled in by younger lava flow. Okay, and that's why we don't see as many craters there. So if we come down here and we look at this moon of Jupiter called Io, and it looks a little bit kind of like molten, rotten cheese. Io looks like this because it is a volcanic moon of Jupiter. It's the closest moon to Jupiter. And so this kind of yellowish surface is caused by sulfur from the volcanic activity. And you see almost no cratering on the surface of Io because it's being constantly refreshed or filled in by lava flow. So anytime you have an impact crater, it's going to be quickly filled in by that the lava flow that's constantly coming from these volcanoes on the surface of Io. So another way you can trace the history of a planetary body is to measure the age of individual rocks. And this was done especially for the moon during the Apollo missions. You could go to the moon with the Apollo missions, collect rocks from different portions of the lunar surface and both the mare and the highlands, which are these kind of white regions that have more cratering. And then you can bring them back to Earth and do something called radioactive dating. Scientists were able to measure the ages of rocks by using properties of radioactivity. Some atomic nuclei are not stable. Remember, the nuclei is the center of the atom. Some of these nuclei are not stable, and they can spontaneously split apart or decay into smaller nuclei. So if you have something on the periodic table, if it spontaneously decays into something that has a smaller nuclei, that means it's something that has a smaller atomic number, has less number of protons in its nuclei. So there's a specific time period called a half-life, during which the chances are 50-50 that that nuclei of the atom will decay into a smaller nuclei. After samples were brought back from the moon by the Apollo astronauts, techniques used to date rocks on the Earth were applied to rock samples from the moon. That's the radioactivity dating. And we can use that to really pin down the age of the moon rocks. You pin down the age of the moon rocks, and then you count the number of craters that are in that area. Then you get this really cool set of data where you can relate the age of a surface of a planet to the number of craters you see on the surface of the planet. Okay, but we can't go out to Mercury with a mission all the time, you know. We can't go out to Mars all the time and bring back material from Mars, at least not yet. Okay, but we can observe the cratering on their surfaces. So with that information, we can see the cratering, and then we know about the age of that planetary surface. But with all that information you just learned, I'm going to ask you to answer both of these questions in your engagement check, okay? I'm not going to write out the words for this engagement check above the little essay question box, okay? Because I want you guys to be sure that you are watching the videos. And one way I can be sure you're watching the videos is to ask you the question inside the video rather than putting it right there for you. Above the question box. Okay, so I want you to answer these two questions for your points for the engagement check. Would you expect, using information that we just learned, okay, would you expect as many impact craters per unit area on the surface of Mars as on the surface of Io? Right here, one of Jupiter's moons with intense volcanic activity. Why or why not? And then, would you expect as many impact craters on Venus as on the moon? Okay, here's a piece of information about Venus. Venus has an average atmospheric density about 50 times greater than that of the Earth. Okay, and the moon has almost no atmosphere. So think about, we talked about the meteors and what happens when an asteroid is falling through the Earth's atmosphere. Okay, so we've got the moon and you're comparing it to Venus with the super thick, heavy atmosphere. So with that, would you expect more impact craters on Venus or on the moon?